So I just want to do the review on interference channels. Just quickly what we discussed yesterday. And so just again to start the model, we had a channel with 2 transmitting terminals and 2 receiving terminals. And as usual, we're writing these channels as conditional probability distributions, y1, y2, given x1, x2. And there's 2 messages being sent by encoder 1 and encoder 2, and they're destined for, separately, for decoder 1 and decoder 2. And we talked about one motivation for this is wireless situations where we might have 2 base stations and 2 mobile stations with which one is communicating, and especially if these stations are near the cell edges, which is of course where most of the area is. If you think about geometry, then there could be a reasonable amount of interference in these transmissions. So this is one example of that. Of course, as I mentioned, a more common case might be to have several of these devices. So you could think of adding cases like that, one transmitter and potentially many receivers who try to decode different messages, so they're different broadcast channels. But this is the simplest version. And one interesting thing is that the information theory for this problem is far from being understood. Primarily because, there is, if we especially look at the basic channel, the additive white Gaussian noise channel model, at least first of all the scalar one, then we reduced the channel to a so-called standard form, and I always forget whether it's A12 or A21, and it's A12, right? We wrote this as A12x2 plus Z1, where we chose here positive coefficients. The reason for the positive coefficient was mainly because we're reviewing this as a gain, but I think in all our bounds that we had, that didn't play a role anyway. So this is an example. So we have these parameters A12 and A21. And the thing is, this here is not really noise, right? It's a code word, and depending on its rate and the structure, you may not want to treat it as noise. In any case, we talked about some approaches to coding for such problems. We talked about different coding strategies and progressively more sophisticated ones in a way. The first was this, treating interference as noise, which I mentioned has even gotten an acronym since about 5 years. That means you're important when you've gotten an acronym, right? That one's really straightforward. Turns out this even, remarkably, I mentioned this can even achieve capacity in some problems, which is somewhat, I think, I'm still surprised by that. I wouldn't have guessed that because, on the other hand, if the rates are high enough, then who knows, right? So then maybe X2N, you can't do much more with it than treat it as noise. And it turns out to be the case. For low interference, so we mentioned for low interference, treating interference as noise is currently the best method we have. Then we looked at time division multiplexing and frequency division multiplexing. That's the most common method, one of the most common methods we use. These are basically the 2 most common methods we use, right? One is to avoid interference, especially in cell, for instance. And then we usually treat cross-cell interference as noise because that's why we have a cellular system in the first place, right? Is to separate geographically users. This works actually very well for intermediate interference. And then the most sophisticated method is to decode the interference, because there we really need to do multiple access interference. We need to use successive interference cancellation receivers or at least decode multiple messages, and that works well at high interference, and in fact there it even achieves capacity. So this achieves the entire region, in fact achieves capacity region if both of these two parameters are bigger than 1, which is something called strong interference. If A12 is greater than or equal to 1 and A21 is greater than or equal to 1. Because what you can show then quite easily is that, as we argued, you know, if the argument goes like this, if we assume that we're operating inside the capacity region, then receiver 1 must be able to decode its own message, obviously. So can subtract it off, divide by A21, and then add back a scaled version of X1 and can recreate this with less noise. Right? That's the whole argument, and that's enough already. And if that's valid for both receivers, then you can decode everything and you get a compound multiple access channel for which we know the capacity region. However, the usual case we run into are these two, namely weak interference and intermediate interference, and there decoding the interferences isn't a particularly good strategy. So what you see happening here already is what happens for, when I talk about relay channel again, there too, there isn't one strategy that's best everywhere, like we've seen for multi-access channels or for point-to-point channels. It seems that we have to resort to putting together many different things, and in some ways, unfortunately, it would be nice to have a unifying method. Then finally, we talked about the so-called Han-Kobayashi region, which I emphasized, really deserves to add Carlisle, because he's really the guy who came up with the coding method. What Han Kobayashi did is improve the decoding method, right? So in that sense, it really deserves all three, I think. Kobayashi. Yeah, Kingo Kobayashi. And there the idea is effectively what they do is put these all together, paste them all together with one change which you need to add to paste this all together, namely rate splitting, right? So and that's what Carlisle already added to the problem. So the coding method is really due to Carlisle. So we have the message W1, split it into two pieces, W1 prime. And then we have, we used superposition coding. So what we actually did is we built up this U1N codebook, and then we superposed on top of that the X1N W1 prime W1 double prime codebook. Fine. The alternative way is just to encode two separate codebooks, so let me do it that way here. And that's the way Kobayashi viewed it. He viewed it as two separate codebooks, which we then, again, put together with some function, which is just additive if you have a Gaussian channel. So then you just add up these. But in general, you'd have some per letter function. So if you do the same thing for receiver 2, transmitter 2, and then receiver 1. So we've converted the problem into a 4-message problem. So 4 messages now, 2 messages here, 2 messages here, and still 2 decoders, but there's one piece on both that's decoded by both. So receiver 1 decodes, of course, W1 primed, W1 double primed, and this is and one piece of the cross term that we decode. So you're adding partial decoding, right? That was the idea, and because of that, you get a lot of bounds. You get 7 bounds, rate bounds for all the 7 important error events from every receiver. So you get 14 bounds, and you do Fourier modulation. You start playing around with this region, and you wind up with a region that has quite a lot of constraints on it. We had one constraint on R1, the region that we found. We had 1 bound on R1, we had 1 bound on R2, we had 3 bounds on R1 plus R2 plus R3. So it's 1, 2, 3, 4, 5. And then we had 2 more bounds. It was a funny looking one with 2 R1 plus R2 and 1 bound with R1 plus 2R2, right? So we wound up with a region with 7 bounds, and that's currently viewed as the state of the art in this area. So a region that has this form that looks like this, you know, bound on R2, bound on R1, bound on the sum rate, and then the 2 other bounds with the funny slopes. Slope minus a half, slope minus 2, right? So those get the 7 bounds. Now I think I mentioned yesterday I added that there was, if you read the Han Kobayashi paper, which is interesting to do, and I mentioned if you look at the footnote somewhere in the acknowledgements, they acknowledge some reviewer, so this is in the beginning 80s, who mentioned that one could perhaps improve this method by adding Martin's coding technique. They just add that, and they thank the reviewer for, you know, for making this suggestion. Now this suggestion was looked at by a researcher from Iran maybe 3 or 4 years ago, who also published it in some conference. It may have even been the local Iranian workshop on information theory, I can't even remember that, and claims that this could improve the region. But you know, it's hard to prove this, I mentioned, because you have so many auxiliary random variables. But it's possible that by also not just doing, you know, this here, but by adding some kind of Martin coding here, because you're broadcasting after all. Notice that this message, we can view it as a MAC from the decoder perspective, but from the encoder 2 perspective, this message has been broadcast, you know, jointly to both. So maybe that helps, but we don't know. There's reasons to think it would, and there's reasons to think it wouldn't. Anyway, there's reasons for both. But it would be interesting if it did improve things, because then that region would at least be viewed as the state of the art in the area. I don't think many people know about that because it didn't get a lot of attention, but there was. And I don't know if he did it in the best possible way, but okay. It was just a few years ago. Okay, just a quick overview of what we did on interference channels. Then yesterday we did quite a lot on relay channels, which was sort of the last topic, was relaying that we wanted to talk about. And so let me review quickly what we did on relay channels yesterday. So relay channels. It's a very rich area too. Again, another one of these problems. So as soon as you get away from multi-access channels, you know, most things aren't known or solved. Everything's open still. So the model is the classic Shannon model, right? Message being that we want to transmit reliably with an encoder over a noisy channel. PY3, so we'll wind up having 3 terminals, so Y3 and W hat decoder, okay. And the addition is that we have a third node called the relay node 2, that gets 1 output and is allowed to send 1 input. Usually, the problem is usually looked at with some delay or negative delay, as I mentioned, where here the usual model is to consider a strictly causal relay. Namely, y2i is some x2i is some function of y2i minus 1. And we may as well add I here, 2i for all I. Right, so there's strict causality in the timing here. And I mentioned there's also models where one looks at something called relays without delay, or you can even make this delay negative so that the relay sees a few symbols ahead of time and then ask what is the capacity then. And we talked about, I mentioned there could be some practical instances of something like that happening, but usually we like to study this because it feels natural. It's the classic model, and also because the amount of delay here doesn't matter as long as it's positive, right? So then all the results turn out to be the same. So that's another reason for studying this case. So if we looked especially at the Gaussian case, that's always instructive to look at separately because it gives you insight. Oh, there's two examples actually. Case one, and I mentioned this, that's again this power of this information theory. If we look at like a network, classic wired network with 3 nodes, we can view the input here of user 1 as being a vector, x11, x12, x1, where the input of this wire is x11, x12, so you're already doing multi-vector communication. You receive y2. Usually y2 might be viewed as being a function of x, just being x11, x2, y, and here again we get a vector. y3 is equal to y31, y32. And we said then we would model this as being y2, y3, x1, x2, we could just model as being p at y2 given x11 time p y31 given x2. So they're just independent channels. That's how you could model such a wired network. Because the noise on all of them is independent and also the influences are independent. So the nice thing just to realize is these memoryless models are much more general than just what you think of like Gaussian channels. They even include wired networks. And that's important to realize because all the strategies that information theory develops for these problems applies equally well to wired networks as it does to wireless networks, or even mixed wireless wire line models like we discussed last time. Gaussian channel is a little bit different. That one is probably something you think of more commonly when looking at these kind of conditional probability distributions. So here we have Z2, this is X1, Y2 goes to the relay, that sends X2, this interferes, and of course usually you would have gains, and if you have fading gains you can add those too and all that stuff. Z3, and this is Y3. Okay, so there's the Gaussian model. That's the full duplex Gaussian model. We can make the model half duplex by adding a constraint to the channel that whenever x2 is not 0, y2 is 0, right? So that whenever the relay is sending something, then it can't receive anything. It's just receiving a constant, a default value, and then you can build that in. And in fact, that perspective leads you to some interesting coding strategies. Namely, sending information via timing. So you can actually send information to the receiver in the on-off patterns of the relay, and not just in the forwarding, right? So these are interesting insights you get directly out of the theory without, without thinking of it ahead of time. The theory gives it to you. And if you look at what you get, you look at the theory and you say, what's going on? It seems like I'm getting a gain. Where's that gain coming from? And if you look at it carefully, it's, oh yeah, it's the timing is sending the information, right? So sometimes it's useful to take an abstract perspective and then try to specialize it to models, and you discover interesting things that you hadn't realized before. That does happen too, right? So that's why also the linking the theory to the practice is super interesting, right? You get new ideas that way. Fine, so we talked about this, and we talked about various coding strategies, the simplest of which is what I called symbol relaying. So this is the simplest kind of relay where x2i as just a constant function of the past output value. So rather than making it a function of all the past, we just use a memoryless relay, if you like, all I. And usually you even choose this function to be time independent. So for example, for the Gaussian case in particular, f of y is usually just a constant times y, where the constant is chosen to satisfy the power constraint of the relay. Right? So this is called amplify forward. I think the first person who information theoretically did a lot with this amplify forward was Nick Loneman in his PhD thesis. So he looked at this in great detail and very successfully, right? I mean, he was looking at it in terms of outage rates, so block fading style channels. Very nice method. Simple method. The nice thing is, it, like I mentioned, it even corresponds to just having passive relays, just mirrors. A mirror would do something like this. Of course, the delay might not be one digital symbol. It might be like 1/100th of a digital symbol, or 1,000th, or whatever, depending on the distance that you have and how fast you're signaling. But in any case, it's a very simple method. Turns out, I mentioned that Amplify Forward is pretty reasonably good at high signal-to-noise ratio, but is pretty bad at low signal-to-noise ratio. And for there, what you can do, though, is optimize this function. And one choice is a modulo, works very well. So I think Mikael Skoglund from KTH, his group, worked a lot on that. The other one is to optimize it. You get sort of sigmoidal functions or variations thereof when you do the optimization. And it helps a lot, by the way. To optimize this function plays a very big role at low SNR. So anyway, that's the simplest method. I mentioned, well, that a simple variation of this is, consider 2-pass symbols or 3 and filter. So that sometimes you'll see these variations having been studied. Okay, second strategy that we looked at is effectively like multi-hopping, but it's a sophisticated multi-hopping. It's decode forward, and it's this method was first developed by El-Gamal and Cover El-Gamal. So he looked at decode forward. And both of them looked at decode forward and also the compress forward method. So they really wrote the first real, substantial paper on relaying. There were several papers earlier by Edward van der Meulen. He started the area earlier, but those papers weren't as, let's say, from the strategies were more basic that they were using. This was real. It was deep in the sense that it's still the state of the art today, basically. These methods. So the decode forward, the idea is that we send in. They also invented this block Markov superposition encoding method in that paper, and the idea is to send in blocks. So you split the message into chunks. So block B equals 1. Just draw it quickly. B equals 2. B equals 3. And then maybe you'll stop here now. I usually went to 4. But what you do is you generate random code books for the relay that by using a joint distribution px2, and then you superpose on top of that using the conditional distribution. For every one of these code words, you generate another code word x1. Okay, and in the first block, so I'll just write those with a little bit bigger brackets. In the first block, the relay, of course, just sends a default message because it doesn't know anything more. And then the source chooses the same default message here in order so that these are jointly correlated, but just plugs in the first message of NR bits. The relay decodes here. So the decode forward rate is going to be the max over all joint distributions px1, x2 of the minimum of basically 2 cuts. The relay tries decode and can decode at the rate x1, y2 given x2, I of x1, y2 given x2, right? Which is natural, the mutual information between this and the first channel output given what the relay knows. Then once it's decoded, hopefully correctly, sends the message. This guy knows or assumes that the relay has decoded the message. It chooses the same subcode like other code book and then plugs in W2. And off we go. W2, W2, and then in the last block we'll not send a new message. So through this we lose 1 block, but as we make the number of blocks big, that doesn't matter. And now we just need the bound of the relay. There's 2 ways to do this. One is we do backward decoding. So we look at the last block and decode W2, and you just get I, x1, x2, y, right? 3. Or alternatively, if you don't want to wait till the end of the block because it's a long wait, you decode after block 2 using sliding window decoding. You decode W1 and you get 2 contributions here. One I x2 y3, and here you get I x1 y3 given x2. right? So use both blocks, then you slide forward. Both methods are interesting. Backward decoding is simple to understand because you see it, you just look at one chunk, it's nice. The sliding window though, you have less delay, right? And so you can start decoding early, and you can think of this as like a streaming method. You're sort of streaming the information. Now when we applied this to here, we found out, oh, this strategy isn't very good for this kind of relay network because we're forcing the relay to decode everything. And if the capacities here are all 1, then you'll only get a rate of 1, right? Because all the information has to go through this path, right? And so we realized, to really cover all these cases, we'll have to have a way of doing multipath routing, right? So how do we accomplish multipath routing? Well, we'll develop a coding method where some of the information gets sent here, and I mentioned the idea is we'll add an auxiliary variable, u, and that will serve to measure the information here, and then we'll superpose on top of that some information that just goes through the direct path. That's the whole idea. And this was called partial decode forward, or is today called partial decode forward, this method. I don't know if that's a particularly good name, but anyway, the name has stuck. PDF. It's not bad, I guess. So we'll do the same thing. We just repeat the whole thing just with PU1, U2. Right? I don't know, maybe I'll draw it anyway. It's useful to keep, once you draw these things, it's like, practicing your music. If you repeat enough, you feel you kind of remember it. X2, 1, N1, N1, and here, so we'll use rate splitting. So here we'll have PX2, here we'll do PU given X2, and then we'll put something on top of this yet, which is PX1 given U X2. So here we'll have the UN with the 1, this index, and a W1 primed, right? So that's what's going to go through here. X2N W1 primed, X2N W2 primed, UN1 W1 primed, of course. W2 primed to get these silly indices, UN W2 primed, W3 primed, right? So that's what's going to go through here, and then on top of that we stuff some extra information with the same sub indices, W1 double prime, so that goes directly through. So this gets decoded right away. X1N 1 W1 prime, so we have to superpose on here to get the right distribution. 2 double primed, and then in the last block, I guess here I shouldn't have sent a new index. 1 X1N W2 primed 1 1, right? Or although we could send another chunk direct. Okay, so the rate of PDF it wounds up to be the max when we do the Fourier-Motzkin elimination, which here is really trivial. So it's a joint distribution on all 3 random variables, min, and here we get what the relay decodes, right? So the first term, right, corresponds to this with x1 replaced by u. Then we'll get a additive term, x1 y3 given u x2, comma I x1 x2 y. In particular, you can easily see if we choose u to be x1, if u is x1 already, then this term will disappear and we'll just recover decode forward. Or alternatively, we could choose u to be nothing, like a constant, then we don't get it, right? Then we get something lower, so that doesn't work. So we have to choose u equals to x1, u equal to x1. Here. Okay, so that allows us to route, and then if we apply this to here, we wind up getting the capacity that we're interested in. Okay, now we applied these rates also to the Gaussian channel. This achieves capacity we saw for the semi-deterministic broadcast relay channel, which is sort of a mixed wireline wireless problem For example, suppose node 1 has a wire to node 2. This is a remote antenna. You have your own antenna, then you have a remote antenna that you can control, and then now suppose we have a multi-access channel to the relay. And suppose this is rate limited. You can ask what's the capacity now. Well, it's given by the partial decode forward scheme. You can prove that you achieve the cut set bound there. Okay, and then we looked, finally, we plotted rates for the Gaussian case. So I just maybe quickly review that. I have the computer here, but I think I'll just quickly draw it. So we plotted a geometric situation where the idea is the source is here, the relay is here, destination is here, there's a distance d between the source and the relay, distance 1, and the cut set bound. So here we had, using no relay, was here. That's half log 1 plus p by n3, p1 by n3. That's what the rate you would get without the relay. Then if we had the relay using decode forward, we got rates that looked like this, which peaked ahead of 1/2, so it looks something like this. And then when the relay is co-located with the destination, we don't get a gain because the relay has to decode, so that's the decode forward rate, and it turned out to be the same as PDF. It's a little bit surprising for the full duplex relay channel. We looked at the cut set bound, which touched perfectly here, which makes sense because if the relay is co-located with the source, we can do 2 antenna transmission. It hugs that curve very closely, but it's not perfect, and then comes up like this, and then goes through something like this. Some rate here, which corresponds to where the receive antennas cooperate. Then I said, if we look at, what we'll look at now is compress forward, which also goes through here, touches here, remarkably enough. Well, actually, I have to be careful to say that. No, it actually doesn't. It goes somewhere, I shouldn't say that. It goes somewhere in between, because I'll explain why. It can't touch there. It's somewhere in between. It goes up like this, goes here, and then, but then is optimal here. You know, and it also does reasonably well on the other side too. So the nice thing about the compress forward, and that's what we'll talk about next, you know, quantize forward or compress forward method, is that it, this is cut set bound, upper bound, is that it tends to be, you know, its rates tend to be more uniform over the region. So I have to talk about this point here in a moment. Okay, talk about that point in a moment. So the interesting points that are easy to understand are, I think, these points here. You know, when you're co-located with the source and destination. Okay, so that's, so usually people like to use the, you know, multi-hopping, but usually they don't use this sophisticated form of multi-hopping where the relay and the source are transmitting at the same time and where the destination is always listening. You can repeat plots like this for half duplex channels, and then the PDF improves on DF. Right. Okay, so just that was a quick rundown of yesterday's lecture. Okay, parts of them anyway. Lectures. Good, so today what I'd like to do is we'll complete the relay channel section where we'll focus on the compress forward, quantize forward method, which is a really interesting method that got a lot of attention recently under the name of noisy network coding. It's basically the same method. So let's talk about that. Okay, so quantize forward. It's another coding strategy for relay channels. QF or sometimes also called compress forward. I'll give you a little bit of a historical reason why these both names appear, and there's no common terminology for this, although I guess I kind of like Quantize Forward the most for what I'm about to show. So the idea here is that if we have the relay, you know, if the relay is far away, let's just say here, can it still help? You'd think, well, maybe not, right? I mean, it's so far away, what's it supposed to do? But it turns out that it could still help because, especially if it's not too far from the destination, so suppose it's close to the destination, because sure, now the relay may not be able to decode, but it can still help the destination. What it can do is, because these are close, it can just ship everything it sees to the destination, and the destination effectively has the relay's signal as a second antenna, a second independent view of what's going on, and that's what two receive antennas are. And if the source even has two antennas, you even get an extra degree of freedom, so you get a big boost in rates by doing this. Another way of viewing this is just suppose it was a mixed wireline wireless network where we have a rate limited link from the relay to the destination, right? You could have that too, a remote antenna from which you're gathering information. Okay, so that's the motivation. And what we'll be talking about is the case where, of course, the relay, if it has an analog signal, it can't perfectly ship it because that's infinite precision numbers. But what it can do is quantize that signal and ship as much as it can to the destination. So that it's a natural strategy, I think, once you view it from this perspective. Okay, so the idea is relay may not be able to decode, or may not even want to. For example, it may not even know what the coding protocol is, right? So it's even nice, this kind of thing, is we don't even have to know whether we're using GSM or LTE or 5G. It doesn't matter. You can just quantize and ship. So the relay doesn't have to know much to do this. It can operate autonomously. Of course, the destination needs to know what's happening, and not only does the relay can operate without knowing what protocol S is using, S doesn't even have to know the relay is there, right? And you might still get a rate boost. Okay, so there are some advantages to this approach, but there are also some disadvantages. A relay may not be able to decode, but it can, of course, always quantize and compress. And of course we'll want to use a vector quantization in general. So we're again going to use block Markov superposition coding. This strategy was first developed by Cover in the Cover-Elgamal paper from 1970 whatever, 9, 8, 7, something like 78 maybe. Although what I'm going to show you is a simpler version of it, which turns out to work as well. And because it's simpler, it's easier to understand and manipulate. So I'm going to choose a simpler version of this called Quantize Forward. So we'll do block Markov superposition coding as before. We split message W into W1, W2, W in B blocks, and we'll again transmit in B+1 blocks, B messages in B+1 blocks. So let me draw what's going on. The source terminal simply generates a code word with just PX1, and then just transmits its messages. That's it. So it's actually agnostic to what's going on in the network. All it does is using a plain old point-to-point channel code, X1N W2, X1N W3, and then this is B equals block 1, block 2, block 3, block 4, and last block is a default code word. Okay, so this is good, right? Relay is just sending without doing anything more. Source. Now the relay, on the other hand, what's it going to do? After the first block, it will quantize whatever it receives to a quantized version of Y in the first block. And then it will use block Markov quantization. So let me describe that. What we'll do is we'll build up a, well, we'll first build up a code. Well, let me write out the way it's going to look. What's going to look in the first block, the relay is going to transmit a default index, of course, because it doesn't know anything. And we'll generate that code book using px2 independently of the first one, right? So it's an independent generation. And then we'll superpose a quantization code book on top of that. py hat given x2. Just classic random coding. So there's a superposition, but the way we're going to use this is going to be different. It's going to be a quantization code book. Okay? So what the relay does is after it sees the output of block 1, it quantizes this to some index. Let's call that, it's called here v2. The reason for v2 is will become apparent in the next moment. And then the next block, it just sends that index, right? x2n v2. Okay? Quite straightforward. And then after that block, it looks at its received output from the two transmissions and quantizes into another code book, namely with the index v2, and the new quantization index will be v3, right? And so on. And that's the strategy. So v2 and v3, y hat 2, 1, and v3, v4. And in the last block, we just send here x2n v4, right? And that's it. That's how the strategy works. Okay, so there's a block Markov superposition coding going on in the relay in the sense of quantize forward, but then quantize condition on what you sent. And the reason for doing that, by the way, is because x2 can affect what it receives, right? What you transmit. Like for instance, for the half duplex channel, if I send something non-zero here, then I see, I've affected my own, what I see. For the full duplex case, that doesn't matter, and then you may not need to use this. You might be able to make y hat to be statistically independent of x2, it's possible, but usually you want y2 hat to be statistically dependent on x2. That's why we're doing this block Markov. And it's interesting to look at examples where you don't need it, for example, to use a larger code book. But okay, that's how we're going to do it. Okay, is it clear how the coding and algorithm runs? So the next thing we'll have to do is, of course, do the error analysis. The first error that can happen is, of course, in the quantization code book, we need to have it big enough that we find a jointly typical y2 hat with the y2 that we've received, right? Because we'd like to take the channel output of the relay and find in this code book a jointly typical y2 hat. So the code has to be big enough to accomplish that. Well, how big does that need to be? The only thing that's new, it's the same as a rate distortion code book, except that we're conditioning on x2. That's the only difference in this. Okay, so it looks as follows. So the relay, after block B, the relay tries to find an index, or a v. Let's see here. So we're at v plus 1 hat, such that we find a jointly typical triple y2 hat bn vb vb plus 1 hat, right? This one it knows, and it should be typical with x2n vb and y2n from block B is jointly typical with respect to the distribution, of course, that we're expecting. Okay, that's what we're looking for. So we'll again have a intersection of events, right? It's the intersection of events rather than a union, because we don't make a mistake if all of the messages here are not typical. What's the statistical situation here? Well, it is the following. We have y2, x2, y to n was produced and x to n was produced, and they're both, these two are typical with high probability. And then we're looking at generating random y to n's across the channel py2 given x2. And we're asking what's the probability that this one happens to be typical with respect to this. It's 2 to the minus n, the mutual information between these two, given that, right? Remember, it's the conditional version. So that gives us our bound. The bound is, well, we'll have to define a rate here. So let's suppose this rate here is R2. The rates of these messages V is R2. So that what we'll get here is then R2 has to be bigger than I of Y2 hat given X2. Right? That's the bound. It's just rate distortion, but conditioned and averaged over the X2s. Okay, so that's the relay bound. Now let's talk about the receiver, the destination bound. We'll see here we need something slightly new that we didn't have before. So what does the receiver do? Okay, so after block B, okay, so in fact we could even do, well, we could do backward decoding if we wanted, I suppose. You know, we could start with this one. Could start with this one. If I started with this one, then I would get R2 has to be less than I x2 y3 given x1, for example. But I don't want to do it here. I want to do let me do the sliding window, you know, forward method. We'll see by doing that we'll get better. It's easier to understand what rates we get. But we could do backward decoding too, actually, here. Okay. So after block B, B equals 2 to B plus 1. I'll go right to the end. So we want to decode, the first, what we're really interested in is decoding, you know, W1 now, right? After this block. And the reason we want to wait is because this carries information about W1, right? Because W1 is related to V2, to which we quantize, right? There's a correlation there, and then we're sending V2 in the next block. Now, this one here won't play a role because we haven't received anything about it, but it's pretty clear here we should look for X2. We're worried about X2, and here we're worried about X1 and Y2 1 hat. Okay, to decode. So let me describe it in detail. So after block B, try to find a pair. So we're going to decode both. W B minus 1, right? So this is B, we're now at B equals 2, so it's WB minus 1 hat. And VB hat. I guess I could have chosen slightly different numbering for the times, but okay, whatever, it's there. Such that, and we'll again do this joint test. So what we want to have is we want to have these typical as well as this typical in the next block, such that X1 in block B minus 1 and WB minus 1 hat. So if I look at that block, that's this one here. And Y and X2 N, this index it knows, number 1, and also here after it's decoded V2 it knows it too, so it knows this index. So this index is VB. And now I also want to have this piece jointly typical, so that will be VB and VB minus 1. I guess this is VB minus 1, right? VB minus 1, VB hat. And of course Y2N in block B minus 1 is jointly typical. Okay, I won't bother to write all the distributions, but the important thing is these are the ones we're looking for, right? The W, B minus 1 hat, and here the VB hat. And so we'll do a joint test. We get typicality here, and here we don't have as much we can test for, so it's just going to be x2 bn, x2n. I shouldn't have put 1 here. I should have put here b minus 1, right? Because we're in block b minus 1. Okay, let me leave it here without, I have to put it in a moment. I'll explain, and as we've already discussed. But the y2 I'm indexing, those are the y's from the previous block. And here we'll have x2n v2 hat, so v, b hat, and y2n in block B is jointly typical. Okay? Does that make sense? Right? Does that make sense? So we're just doing a joint typicality test. It has to be typical here and it has to be typical here. Right? So there's an intersection of events for an error to happen. For an error to happen, I have to have an intersection happen. Now again, to make these two error events, the event that this happens to be true and this happens to be statistically independent, I again, for sliding window decoding, I should actually make all these blocks independent by choosing different random codes for every one of them, right? So formally, I should worry about this, and you see you're starting to get a lot of indices, coming into here. I guess I already added it here by, for some reason, 2, 2, 2, 3, right? It's clear. So the reason we choose a different random code each block is just to make these independent. I think for backward decoding you don't need it again, but it's more of a formalism just to make sure that the proof goes through. We can certainly do random coding with this approach. Okay? Okay, so what kind of rate bounds do we get? Here we'll see there's a slightly new piece that appears because there's a joint independence. Now, since we're decoding two pieces, it's like a multiple access channel. There's 3 possible error events we have to worry about. This one is correct, this isn't, this one's correct, this isn't, and both are incorrect. So we'll have to check 3 bounds. So let's go through what those are. So let's say W, let's look at the case where W hat B minus 1 is equal to WB minus 1, but VB hat is not equal to VB. Okay, so what's going to happen? If that happens, this one is the correct, so I guess, well, anyway, this one here is going to be the one that was actually transmitted, but this one here is different, right? This one here is different. And this one here was chosen based on x2, right? So the statistical situation we have looks as follows. We have 3 that were produced jointly, x1, x2, but x1 and x2 are independent, y2. And y2n and x1n are here, and x2n was produced here, and the y2 hat was chosen based on x2 only, right? Right, so what is the rate bound here? Well, it's just the one we always had, so R2 has to be less than the mutual information between this and this given that, right? Y2 hat, Y3, this should have been a 3. My apologies, this is a 3, right? Everything here should be 3. Because here we're testing at the receiver, so that should be the receiver's, sorry. This should be the receiver's signal, right? Because we're testing at what the receiver knows. X1, Y3. right? That's the mutual information, that's the probability that this y2 hat happens to be jointly typical to the rest. Okay, just by the same rules we've always had. Now we add that here. Here it's easy. It's just going to be ix2 y3. You know, right? So plus ix2 y3. Okay, so that's the first error event. Now let's go to the next one. Let's do this one isn't, but this is equal to. So now that doesn't appear here. So we'll just test this. So that's only when this one here is independent. Now this one here was chosen independently of everything. So that bound is relatively straightforward. We'll just get r less than I of x1, x2, y2 hat y3. That's what we'll get. Okay, that should be clear, right? Because this is the only one. Now the interesting one will be when both are incorrect, because now we'll of course have to take both into account again. And so, okay, let's see what happens. So if they're both incorrect, both invalid, now we have a funny situation happening, something we haven't had before. In this typicality test, both of these are independent of the rest, and they're independent of each other. Okay, so we have to think about what's happening here. So what's happening here is a situation as follows. We're effectively having three independent things happening, namely x2, y3, and x1 is being produced independently, right? And y2 hat is being produced independently. Well, it's dependent on x2 actually. So here, this one is actually being produced dependent on x2. Okay. But the important thing is here that we don't just have one that's independent like we've had up to now, we have a separate one appearing too. So this corresponds to a case, if we didn't have the conditioning, this corresponds to a case of asking a question like this. Suppose I have three sources, px, py, pz. What's the probability that all three of them happen to be jointly typical with respect to some joint distribution? Okay, what is the probability of that? And that's not too hard to test, because so the probability that, let's just do it quickly, is typical with respect to some joint distribution. Okay, that's just going to be the sum over all sequences that are jointly typical with respect to the joint distribution times the probability of that sequence, right? But the probability of these sequences is pxn, x1n, xn, p, yn, yn, p, zn, zn, right? And what's this probability? Well, if this is jointly typical, it's marginally typical. So this is 2 to the minus n h of x approximately. This is 2 to the minus n h of y, 2 to the minus n h of z. And this, the number of values in it is about 2 to the n h x, y, z. So in fact, this probability is approximately given by 2 to the n h of x plus h of y plus h of z minus h of x, y, z. Right? That's what it is. And of course, if we have two of those, then that's just the mutual information. That's how you get the mutual information. Now we get something a little bit funny. We take all the independent minus the joint. Okay, so you have to watch out. That case is exactly showing up here. In fact, it's showing up a little bit more complicated because this is generated from x2. So it's even generated conditionally. But to treat the conditionally dependent version we can do it the way we've done up to now. You add conditioning. Okay, so that's just a very quick explanation of how the rates are going to look like. Okay, so what we need to test for is, first of all, we're looking over a sum of rates, so it's going to be r plus r2 right? Because it's going to be union over both those sets. And now the probability that will happen to be typical here. What is that here? Well, it's going to be h of x 1 plus h of y2 given x2. I mean, I could have written h of x1 given x2, but they're independent. Plus h of y3 given x2 minus h of x1, y2, y3 given x2. That's what the answer is. I could have written here given x2. Okay, do you see it? That's why I get this triple. These things are subtle, right? So it's important to remember when you have these tests. So this is new. This is something we haven't seen before. It isn't no longer just a plain old mutual information. We have to do this generalized mutual information is what we have to work with. So this is kind of like a generalized mutual information. Okay, and then we'll get the contribution of the other term yet too, ix2, y3. That's this. Okay, that's it. So this is the rate region you get. At the moment it looks kind of ugly, right? So we want to simplify it, but after all, R2 is still an open parameter, so we can still manipulate it and try to simplify the rate expression. Now to do that, we could massage this here, and we can show after just a couple of steps, like you can show the following. This thing here is h of x1 given x2 cancels this. Here we have h of y3 minus h of y3 given x2, that cancels that. And after two steps you wind up with the following expression here. This is x1, x2, y3 plus plus I of y. Let's see what it is. Just looking at if I want to write it out the other way or not. No. So x1, y, let's just like x1, y3, y2 hat given x2. What I was thinking of is here I can write this as a mutual information, you know, but anyway, I wanted to leave it. So anyway, we get this. Okay, so we get this. The important reason I wanted to write it in this form is because I'm getting this piece, which is what I'm looking for. That piece I'm looking for. So the important pieces, and also here, if we look at this expression, this is the mutual information between x1 and x2, which is 0 plus x1 and this given x2. Okay. Now why is this piece is interesting? Why is it interesting? Take a look at what it means. This is the mutual information from a 1 antenna to a 2 antenna receiver. In fact, if this was y2, you would exactly have given the relay's signal to the receiver. So this shows you that we're not giving the relay's signal to the receiver, but a quantized version thereof. Right? So this expression is really interesting. It's related to the cut set bound, just that we have y2 hat rather than y2, which is the quantized form. So that's the intuitive explanation of this, and that's exactly what it means, right? So that one we were interested in. Now the rest, what I have to do is I have to subtract this from this. So I have to subtract this from this, and if I do that, I get the following rates. So let me do that first, then maybe I can say a few words about the historical thing, but we've already gone on a little longer. So on the other hand, we don't have a break, right? So you have to suffer at least for another little while. Anyway, if we subtract those two off, we get the following region. So this here is RCF, or let me leave it without that yet, because then I want to do the opposite. R is the minimum of the first term, I x1, y2 hat, y3, x2. And then I x1, x2, y3. If we had this, we would be, I mean, this looks like cut set bound up to the quantization, but there is a little bit of a loss here. Minus I, and this loss is interesting, y2 hat, given everything else. Okay, so in other words, after I subtract this term here from this, I get exactly that. Okay, that's that second term. And then we still have the constraint that the R2 we had those two constraints, right? R2 had to be bigger, so subject to I y2 hat given x2, which has to be than R2, right? That's the it has to be less than that term there. So that will be this longer term, I x2 y3 plus I y2 hat. What is it? X1 y3 given x2. Okay, this is what we have up to now. Okay, so we get the rate, which has sort of like almost a cut set interpretation, unfortunately with a little bit of a loss on one of the rates, but this definitely looks like what we had. It would be great if this was y2, and if this wasn't there, then we would almost achieve capacity, except that x1 and x2 are independent. They're not joint right here, right? Okay, so that is another constraint. Okay, it turns out I can simplify this here, and the way you can show that you simplify this is you can show that this constraint is the same as, just by rearranging terms, you can show that this is the same as y2 hat y2 given, so this term given x1 x2 y3 less than I x2 y3. Oh, that's easy, right? In the sense that all I have to do is take this side and subtract it off from this side. So then I get this constraint. Now this form is a little nicer than this one, because look at what happens. So what I can do now is the following. Suppose this is violated. Suppose this is bigger than that. What's going to happen? Well, if this is bigger than that, this term here will be less than this minus this, right? And if this term here is less than this minus this, that means the rate has to be less than I x1 it. So if bound violated, then we have R is less than I x1 y3 minus I x2 y3. But that's I of x1 y3 given x2. And we know how to achieve this. Namely, just don't use the relay at all, right? So if this bound is violated, we can still achieve the resulting rate, is the main point. So I may as well just drop the constraint, right? I don't need this constraint. I know I can still achieve the rate even if the constraint is violated. So the whole rate just becomes everything without this constraint. And that gives us our compressed forward rate. The compressed forward rate is equal to the max over all px1, px2, and py2 hat given x2, y2 of that rate. That's the quantized forward, final quantized forward rate. Okay? So it's a bit more complicated, right? We needed a couple new things, but we wind up with an expression that looks nice. It's almost a little bit like cut set with a little bit with a loss. Okay. Now a few words about this region. This region, the way it's presented here, was first appeared, as far as I know, in a paper in 2005 by students of Abbas El-Gamal and some of his doctoral students. Before that, the rate region looked different. So if you look in the Cover El-Gamal paper, there's a couple of differences to what I just presented. First, they didn't do this joint decoding in that paper. What they did is a step-by-step decoding method. And they wound up with a region that looks a little different than this, but turns out to be equivalent to it, but looks a little different. And they also used not the simple block Markov coding scheme I showed you, but they used Wiener-Ziv coding in their paper, which turns out not to be necessary. So what they did in their original paper from '79 is something, the coding scheme was more complicated than necessary because they were trying to build up something intuitively. In the end, though, like, this is the preferred form, I would say, today, at least from the rate expression, even though it's a little harder to derive, but not that much harder, but a little harder to derive. And the reason, usually the method that they used is called compressed forward, because you needed to use Wiener-Ziv encoding, but this one's simpler. You just do quantization and forward the quantization bins. So the second thing to observe here, note that the vector quantization has no distortion constraint on it. So it's not the usual kind of vector quantization. It isn't done under the distortion constraint. It's without a distortion constraint. It's a quantization without any distortion constraint. Interesting. A little bit different in style. Thirdly, well, okay, so we'd like to, okay, so what we should do now, I guess, is apply this to the Gaussian channel. So let me do that, because I'd like to show you that we get that rate point here that matches the cut set bound. Oh, another point to make, so let's see, remarks. One, quantization, vector quantization has no distortion constraint. So it's a little bit of a different style of distortion. Now that might sound funny to you, but where the constraint comes in is here, right? We don't want this to be too big. So for instance, for a Gaussian channel, if I could choose y2 hat to be y2, but if I did that, this number goes to infinity, because for Gaussian channels, y2 has infinite precision, right? It's a real random variable, continuous random variable, and then if I choose y2 hat to be y2, I would get infinity. So the distortion constraint sort of comes in through this loss term. It has no constraint other than via rate losses. So in some sense, the distortion constraint is the mutual information that you're losing. Okay, so it's kind of funny. It's there, but it's not, you know, in a different way than usual. X1 and X2 are independent, and so this is one of the, I think, most severe weaknesses of this method. The inputs are statistically independent. Okay, so that prevents you, especially for to do beamforming, which might be especially not so nice if you have multiple antenna transmitters, right? So we might have multiple antenna transmitters here, multiple antenna transmitters here, but no beamforming between them, okay? So that's one disadvantage of this method. And I've often thought, you know, is there a way of fixing that? Because in some sense, the transmitter knows something about X2, right? Because the transmitter knows, suppose there wasn't much noise, then the transmitter would know relatively well what the relay is seeing, and it will know relatively well to what it's quantizing to, right? So maybe there is a way of building up a version of this where we do get some correlation across. But as far as I know, no one's ever been able to come up with something like that yet. It's interesting to think about. Okay, because that would be helpful, especially for wireless, because the beamforming sound is only a power gain if you have one antenna, but if you have multiple antennas, it's a degree of freedom gain. You need, the beamforming is like increasing the rank. You could potentially increase the rank of the channel that way. Okay, those two comments. We could quickly look at the semi-deterministic case. To see to see this happen in action, this kind of effect. Suppose we have a semi-deterministic channel, which you'll remember is y2 is some function of x1 and x2. Okay. In this case, we can choose the y2 hat to be the best thing that we would like to have it, namely y2. And why? Because we still have the Markov chain. Like we have this required Markov chain. So here that we do have that x1, x2, x2, x. Well, they're independent actually. So we have x1, x2, y2, y3, and then x2 and y3 produce. X2 produces. I apologize, x2 and y3 produce y2 hat, right? And we can't necessarily choose, let's see here, I have to be careful how I do that. oh no, I can always choose this. Actually, I take it back, so we don't need the Markov chain. I can always choose y2 to be y2 hat. I can always do that. I thought I have to worry about a Markov chain, but I don't. Okay, we can choose this. Now, as I said, for the Gaussian channel, that's bad. But for the semi-deterministic channel, what's going to happen is if I choose y, here you'll even see that since x1 and x2 define y2, this is just 0 anyway, right? And then the best choice for y2 hat is y2. You see, that's why we do it. And then it looks like we get the cut set bound, right? But do we? And the answer is no, because x1 and x2 are independent. Okay, so we achieve cut set bound, or maybe I should put it this way, we achieve the, in quotation mark, cut set bound rate but with independent x1 and x2, and so that because of that it isn't the capacity necessarily, because we're transmitting with independent transmission. So if I take that example, again this wired example, source, destination, MAC, remember PDF achieved capacity, but it achieved it because we could do the beamforming here. This method achieves x1, y2, y3 also the same rate, but because both transmissions are independent. Okay, so we lose as compared to PDF, partial decoding forward. It's not as good as partially coded forward in general. Finally, and now we're getting towards the end anyway, and I don't know how much sense it does to do much more. Let me say a few words about the Gaussian channel. First, I'd like to show that you get to that point here that is the single transmit antenna to receive antenna case. So let's look at the additive white Gaussian noise case with one antennas each. What we do is we'll choose, well, we don't want to choose y2 equals y2 because this will give us 0 rate. So we choose, of course, a Gaussian version where this here is 0 mean Gaussian with variance n2 hat. And if we plug into these equations, what we'll see is that the rate looks as follows. We'll get 1/2 log of 1 plus p1 d squared 1 plus n2 hat plus p1, where the best choice for n2 hat turns out to be p1 1 over d squared plus 1 over p2 divided by 1 minus d squared. Okay? That turns out to be the best choice. Okay, so what you see here is the maximum ratio combining gain, right? The direct path that you get information from and the path from the source to the relay, right? With some extra noise due to the this is the quantization noise, this is the noise of the channel, the relay's receiver plus quantization noise. So if I can make n2 hat go to 0, I have the one transmit antenna, 2 receive antenna rate, right? Which is just, yeah, maximal ratio combining. And it's easy to see when that happens. Well, when does n2 goes to 0? If either d goes to 1, of course, or p2 goes to infinity. Or, of course, if p1 goes to 0, right? So there's various cases. Or d goes to infinity, but if d goes to infinity, then the relay is infinitely far away and won't help at all, right? So there's, yeah, okay, we could add it. But the one we're interested in is this one here. D goes to 1, right? Then this goes away. D goes to 1. And anyway, if you plot this curve, you get that green curve. So you touch here, here you're lower, y, You still get a gain because the relay is quantizing and sending, but a gain x1 and x2 are independent, so we can't get the beamforming gain here. So we do get a boost, and I think even these two rates are identical, if I'm not mistaken. If I drew it right, I think these two green points would be at the same point. So looking at these things in detail is rather interesting. Okay, so these are the 3 or 4 basic coding methods for relay channels. Symbol relaying or amplify forward, decode forward, partial decode forward, which maybe we can put together into one, but anyway, considered to be 2, and this quantize forward scheme. Okay, those are the 3 basic methods. There is nothing better. This is still the state of the art today on the capacity. So there's a relatively big gap here. The cut set bound is still the best bound for this problem. I can say a few things about this. So recently there have been improvements on this channel where you have a rate wire to the destination. So for Osgur from Stanford, along with some of her postdocs and co-authors, has been able to improve the upper bound for that problem, which seems quite good improvements, quite strong improvements. However, those results don't apply yet to, the full wireless kind of scenario. But there is progress. The progress is it takes quite sophisticated math. It's a lot of geometry inside typical sequence sets. It uses blowing up lemma kind of stuff, or transportation inequality kind of bounds. So it seems to be quite sophisticated math ideas that were used. So this is current work going on right now. It's really interesting to see if one can't simplify that, because the math is pretty tough to figure out, and I think if one wants to extend it to more general classes of relay networks, that would be quite important to try to simplify that. But we'll see how that develops. Anyway, it's another step in understanding that's been recently developed. So it's a little bit exciting, that result. That's one comment. Second comment, of course, we're not only interested in 3-node networks, we're interested in networks with many nodes, right? So we can ask since about the year 2000, so in the past 15 years or so, 15 to 20 years, there's been a lot of activity in trying to take these methods and apply them to larger networks. Okay, so decode and forward is basically multi-hopping, so that extends in a relatively straightforward way to larger networks. This method also extends relatively straightforward to networks. In fact, it's kind of nice. Remember what every relay does? So if you have a big network, what every node here does is just quantize and forward, right? So the relay will just take its signal YR, say it's the kth node, YKN in block B, convert it to Y hat K in block B, and then send off information. And just keep going. Quantize forward, without knowing anything else going on in the network. So all the relay nodes can operate autonomously, and you can derive a rate region for this. So this is today called noisy network coding, but that's the strategy. It's exactly what we saw here. It's the same thing. The source node just merrily transmits its block. All the relay nodes quantize forward. In fact, you can even have multiple messages now in the network and multiple destinations. The relay nodes just quantize forward. The receiver nodes have to do a lot of work here. They have to do a joint typicality test or maximum likelihood decoding given everything that's happened in the network. So the complexity here is moved to the receiver, okay, of a network. Any receiver has a lot of work to do, whereas decode forward, all the work is at the transmitter. Okay, and that matches again this picture. Decode forward is more of a transmission-based strategy, so the transmitter is complex, controls all the devices. You're controlling all the devices. Quantize forward, all the devices are uncontrolled, and the receiver has to do all the work in decoding. So they're two very different philosophies of networking. One is more transmit based and one is more receive based. So it's interesting to think about it from these perspectives, I think, because well, that's why these methods were developed for large networks. It's easier to understand them in this context. Okay, and sometimes you want to put both together, like in the scaling laws. The scaling laws, what was done is you have this geographic grid, which you then subdivide, but all nodes here use decode forward first to send messages. One node is chosen in every section to start controlling all the others. Then at the next phase you transmit over long hops. Then all the nodes here quantize and forward to one common node, right? That decodes everything and then sends again all the information out to the next nodes, and then you build up a hierarchy of this. But the point is the organization is like basically based on decode forward for local transmission and quantize forward for local reception. Okay, and then you build that method up. That's how it works. Hierarchically though. Okay, well, I don't know if it makes so much sense to go through the details of that. I mean, I had prepared, but I have the feeling, like, we've been going on so long right now that that I don't think that writing out any blocks and writing out any equations makes so much sense at this point. But you have to tell me. So we have various options now. Either you ask questions, or I have also stuff here. I have slides as well, so then you don't have to write anything, and I don't have to write anything. Or we could go on, and I could describe the decode forward for, multi-hopping or the noisy network coding, at least the rate regions I could write out quickly and try to explain intuitively. But otherwise, I think I should, I'm not sure I should continue. I don't know if it makes a lot of sense. I have the feeling there's a little bit of overload.
You mentioned that
yeah.
There's no distortion constraint, but it appears here.
Yeah, yeah.
Right? So does that mean that we should essentially be using very, very less number of bits essentially, because it's appearing as minus, y hat is appearing.
Well,
so we should be, actually there should be a lot of distortion in some sense.
Well, yes, but on the other hand, it's the trade-off. Here you want it to be very precise. Here you don't want it to be too precise, you see. So we do want y2 hat to be as accurate a representation of y2 as possible in order to make this go up. But then we pay a price here. You see
whichever is the dominant.
Exactly, it's a trade-off. So there's an optimum choice of y2 hat. In fact, the optimal y2 hats are in general not Gaussian random variables. Okay, that's done just for convenience of calculations. And you'll especially at low SNR, you shouldn't be choosing this to be Gaussian. You should be choosing it to be binary. That works the best, in fact. Quantization to binary to bits. So there's a lot of interesting issues. If you were actually decided to implement compress forward, there's a lot of interesting issues that appear. One is, of course, the choice of quantization and so on. It's quite open what that is. Most people like in the last 10 years, there's been a lot of more movement to get a lot of movement away from optimizing this to the nth degree for certain channels. Instead, people have found scaling laws more interesting, and they're more fun because you have a little bit more freedom to work with. You let the SNR go to infinity and things simplify, right? Or you let the number of nodes scale and things simplify, and it does give you a different kind of insight. So that not many people have worked on like optimizing this, or even looking at general properties of what this optimization looks like. There has been very, very little research on that, mainly because of lack of interest, I would say. Now, we can maybe say a few words about this relay. Suppose you wanted to actually build a network, let's say with some implement with some motes or with some, in a real system as an experiment, this compressed forward method. People have tried this, but once you start thinking about it, you realize that it's a very different kind of design. First of all, the protocol stack changes in a way. So decode forward naturally matches the IP protocol stack. You decode something and you pass messages up with like tags, right, which you take out, and then you go through the network layer, you go up, and then you come back down by rerouting and stuff, right? So there's a very natural thing. When you're quantizing, there are no messages, right? So there's no tags that you're getting, nothing like that. You're not decoding anything. All you're getting is this, index y2 hat, right, that you're quantizing. And so what do you do with this index? Right? I mean, what does the relay know in a network what to do with it? Not a lot, right? So somehow it's not so well matched to when you're doing this quantize forward, you need to usually know something about the network structure in some way before you even do it, right? So if you don't have that structure and you don't know where you are, or who, this node doesn't yet know who should I forward this to, right? So in the protocol itself, you have to set it up ahead of time so that you know that everything I'm receiving now I need to forward in that direction. So it takes a little bit more thought in how to make this quantize forward scheme or noisy network coding fit into our current way we build wireless networks, even ad hoc wireless networks, which is where we'd like to use this sort of thing. And again, it is really useful. Like, it's not that it'll gain you a lot, especially if the relay is close to the destination, because then you can start having, two receive antenna gains. The gains are degree of freedom gain. So anyway, that was a long spiel, which I don't know if it really answered the question. Any other questions or comments on that?
For relaying, there is always a privacy concern, because if you are going to...
Yes, so relaying, so the point was relaying is always a privacy concern. That's true, but to me, like, the privacy, if you do secret key cryptography, there is no real privacy. I mean, it's the same problem. So where do we build in our privacy and security? Do we build it in using, with keys, which is the usual way today? Then everything's fine, right? Then there isn't really a privacy concern. If we use physical layer security, or if we're sending stuff without protecting it first, yes, then you have a privacy concern. And it is a concern because, of course, many protocols don't necessarily build in the security right at the very start. It's not end-to-end. But if it's end-to-end, all this is fine. There's no privacy concerns. You see, so it depends a little bit on your perspective. To me, that isn't a showstopper, but if you're using a protocol that is sending data in the clear, you have that privacy concern anyway, you just don't know you have it. Right? I mean, it's true, because if this is a privacy concern, well, even if the relay isn't there, you have that privacy concern because you can just put one there.
People are saying my battery will be draining without me.
Yes. Yeah, okay. So this is the more exactly. So the energy concern. Why should I cooperate? Incentives for cooperation. So this was a concern already, 20 years ago or even longer. Especially once you start sharing, absolutely, why should I help you? So you would need to build up some kind of incentive system, because in the end, the idea here is that using these methods actually boosts rates for everyone, right? However, you might have people who aren't willing to play along with it, so you have to build in some kind of incentives. That's right, and how you do that is an interesting question. So that is more of an economical kind of study, I think. So it's a game theoretic type of question. Of course, you could build it into the protocols by preventing people from turning off certain things, but of course, physically, they can always turn it off, right? So I view a lot of this, you could have a fast impact with these ideas is in a dedicated network or in a dedicated environment where you build your own little network to accomplish something. Then of course you can tell all the nodes what to do. And that's a different kind of application like having the mobile nodes share information with each other. But that's an interesting perspective too. I think people, like if you look at, especially, depends what country you're in. A lot has to do with culture. So in the U.S., people don't seem to be very concerned about privacy, right? I mean, everyone puts everything on Facebook. Everyone shares all sorts. As long as it works, they allow these experiments on autonomous vehicles. They have crashes. Everyone just shrugs their shoulders and says, "Okay, let's move on." It's kind of strange. Like, I mean, different. Whereas in Germany, I mean, privacy is a huge thing. The laws are very strict, and you could argue at what point does that become, counterproductive or not. But that depends a lot on the culture you happen to be in, right? So, for example, all these autonomous vehicle tests, I think, are unthinkable in Germany. I mean, they wouldn't even allow this because the safety is just so questionable. Meanwhile, in the United States, you have states opening up their roads to do this testing, and the companies are just doing it, and nobody's making sure that it's safe, right? It's a completely different culture, right? So that's why I say privacy, it'll depend a lot on where you implement this, I think.
How do you feel being from Canada and now living in Germany with this privacy issue?
About privacy issues? Well, I don't know. I have mixed feelings about it. Yeah, I guess I find it comfortable to be in a country that takes it seriously, being in Germany. In Canada, I don't know, because I haven't been there for many, many years, and I left before even the internet really came along, so I don't know exactly how people feel about it there as compared to the US, although I suspect it's very close to the US. I do find it comfortable to live in a country that takes it quite seriously, at least that aspect. I think, on the other hand, in the US, of course, the things progress faster in terms of technology because there's less constraints put on the technology in the first place. So, okay, that's an advantage for technologists or people like us who also profit from companies who work on communications in our research and in our funding. So there is that trade-off, I think.
Can you take an example of a channel with feedback, let's say a Mac with feedback, and see how the
you were saying
how things change when you have feedback there?
Feedback. So feedback's an interesting issue, of course, because there's two main kinds of feedback. There's the feedback that is loved by network information theorists, like the feedback that's quick, right? So if we think of channels with feedback, even the point-to-point channel with feedback is interesting. XN, YN. And, usually we love our, noise-free feedback, which, of course, in practice, usually that's not what feedback looks like, except for control problems. So for control problems, then this full feedback does make some sense. There you're controlling a plant. Usually the plant reacts slowly, so sending back a lot of feedback is reasonable. Okay, but the usual feedback, so the question is, are you interested in control or communications? You're interested in communication. For communications, usually the feedback is only 1 bit for a whole block, right? So usually you have very limited feedback. So then we're really getting into two-way channel problems. So a problem where we have you can decide to add noise or not in the feedback link. So if we had YF given XF maybe, so this is the feedback link. So here's now the receiver. Right, that's a little bit of a different problem. Usually we model feedback links as being noise-free, right, usual model. Because you're using the control channels, which has a powerful code, very low rate. Okay. So classic situation where we have ARQ and better, hybrid ARQ refers actually to the combination of ERQ plus coding. So there's the sort of, or feedback plus coding, how you do the forward coding. So yeah, you were asking about this yesterday. I mean, the usual model that you consider in practice, very important in practice, is that you design a system for, let's say, a fading channel. So you have some fading state. So you're sending information. So your channel is really yi equals h xi plus zi is probably a reasonable model where this stays constant. So random but constant over a block, right? A block. So I equals 1 to t, let's say. So that would be the, say, coherence time of the channel. And then usually what you do is you transmit. So the usual strategies are you send, like, let's say, for half the channel symbols you decide to send a code word. And then you wait for the feedback bit, and if the feedback bit, this is the case where we're getting the feedback within the block. Of course, there's problems where you have to do it across blocks. And then you get the feedback bit, and you decide whether to send more or not. And if you're using hybrid ARQ, you just add more parity checks, right? So you might add xt over 2 plus 1, xt over 2, up to x3t over 4, let's say. And then you wait for it again, and we're still leaving open some room to send more bits. But if you get an OK, you will free up those resources. You won't use them anymore, for example. And you might schedule someone into that block now. The scheduler might put someone into there. Is this the best method for these channels?
Let me define my question. I was more interested. So I have a channel with memory.
Yeah.
Okay. And
memory.
Basically, I'm interested in designing my code book, or finding achievable rates for a channel with feedback.
Yeah.
So how does my coding strategy change? Let's say, just take a very simple, point-to-point communication, right? And I'm randomly generating these code words, sending over this channel, checking for joint typicality, and then. But if I have a feedback, then how does my coding strategy changes?
Well,
can you just
this is a change, right? With the feedback, you can do methods that adjust power levels and rates. But anyway, I think you're after something where it's maybe a little bit more sophisticated. I mean, once you get to multi-access and broadcast channels, there things definitely change, right? Because and if you use, so for the Mac or broadcast channels, and especially if you're talking about MIMO, things definitely change, right? Because with the feedback, you can, especially if you have channel state information, if you...
In practical schemes, I understand, how you, you getting this CS information and you use that. But I'm just thinking in terms of, ergodic, a capacity of a fading channel with memory and
so information theory for it.
Yes. How would I choose my code book design, and how would I show that this will essentially achieve? I'm not talking about
strategies. You're talking about information theory. Well, okay. So there's not much, but I can tell you my take on this. So there is. There's a model called discrete memoryless network, discrete networks, so networks within block memory. I kind of like this, but it's never really caught on. But the information theory for these problems is for a certain class of these problems, which I think is interesting, block fading, feedback within a block. I wrote a recent paper on this, 2014. It's never really caught on in interest. I understand the reason why, because the information theory for these problems looks daunting. But you can come up with an information theory for the problem. So the models that I use here, it looks as follows. What you do is you divide the time into chunks. It's the way we usually use networks, right? We send in chunks. let's say, of length L, 2L, 3L, and so on, and we say the network has memory inside a block. That's why in-block memory. And then it changes randomly across blocks. Now there's two interesting perspectives information theoretically for these problems. One is that the memory is inside the block, right? And one is that the memory goes outside the blocks. Now if there's memory only inside the block, and the motivation for doing this is usually in current systems you schedule communications into certain time and frequency resources, and then the next time you get a new time and frequency resource, maybe much later, where the channel is chosen independently. But inside this you have memory, either OFDM or a constant power level and so on. So you can develop an information theory for these problems. However, because the memory is inside the block, you wind up with rate expressions that use adaptive code words. So even for the feedback problem, with memory, you can write out the capacities. Suppose I have memory in chunks of length L, then the capacity is given by an expression that looks like this. It's the same, so let me see here. Suppose it was a point-to-point channel with such in-block memory and feedback inside the block. Then the capacity without feedback inside the block would just be this. Right? Px1L, you maximize the probability distribution over all probability distributions on the inputs in vectors, right? So it's basically a vector input-output channel. Now if there's feedback within the block, which is what makes it interesting, if the feedback only happens like with ARQ across blocks, then the capacity is still this. And feedback comes down to simplifying the coding schemes, which is the classic, Shannon's classic theorem. Feedback does not increase the capacity of a memoryless channel, but it can simplify the encoding. And that's what ARQ will do for you. It can't do more. However, if you have fast feedback, like fast power control within a block, then this optimization changes that we have to optimize over all adaptive code words. What is an adaptive code word? If suppose your channel was binary, input, binary, output, the adaptive code word is a tree. Like if you think of what is a code book, let me write the code book as just a line which is labeled, right? X1, X2, X3, X4. And we have a lot of these lines. An adaptive code word is you place every line, like this is line 1, this is line 2, you have to place them with trees. Okay, so this is the tree, and it's a binary tree if the feedback is binary. So it's just a tree of depth 4. Every one of these edges is labeled, just like here, 0, 0, 1, 0, 1, 0, 1, or 0, 1, 2, 3 if it's quaternary. So you place every one of these lines with a tree, and then you have to do random coding over those trees and do typicality coding. That is this is the capacity of this point-to-point channel with in-block memory. So there is an information theory for this. However, it's quite a lot more complicated, and in terms of bridging this information theory to practice, very little is known. Here you use linear codes, we have all sorts of constructions. We have almost nothing here. It's just complete open ground, and I don't even know how much you will win from this insight, in the sense, I'm not sure, I don't know. But you get my point. All I'm doing is building in the structure of the problem, and I can do typicality testing on the trees, and I will get exactly this rate, and I can show this is the capacity. This is the capacity, so max P is the capacity of a point-to-point channel with in-block memory of length L, with independence of the then you have a new chunk with new in-block memory. So this is the capacity of the fast power control channel. There it is. But now find for me good distributions, right? And how do I convert that into real strategies? Okay, so this is like from 2014. It never really caught on, which I understand, because it's very information theoretic. I think it has maybe 8 citations. as far as I know, that's the information theory for, these block fading channels. If you permit memory inside the block, I mean, it has a full answer. Even point-to-point channels are interesting here. What kind of strategies do we use? Can we prove that they're optimal? Can we somehow how do we build these trees? Right now, the way these trees are built is just using ad hoc approaches, intuitive methods for fast power control. You change the power levels and so on but it would be nice to prove formal results on this. So anyway, my main point is there is an information theory, but I don't know how useful it is at all.
Can you take a toy example of this compress and forward to just give a feel of what is a typical, how much compression typically?
Yeah. No, it's interesting.
A feel of that.
Well, I think the simplest. So if we want to stick to Gaussian, which probably is of the most interest, I mean, probably the best thing to start with is...
But Gaussian is bad, right? I mean, you don't want a chat.
No, Gaussian is bad?
Meaning,
why?
you don't want to quantize things.
I'll give you a quick example. Let's do the symbol relaying with a scalar quantizer. Just choose this function to be a scalar quantizer. And guess which kind of quantizers are good? Well, like modulo quantizers, for example, or a simple scalar quantizer is demodulate and forward, right? So even these simple symbol level relayings, you could optimize a scalar quantizer and then encode. I mean, usually we'll use scalar quantizers. Building vector quantizers makes the decoding very hard. This is probably the simplest compressed forward scheme you can think of. Scalar quantizers, you get bits, you convert the bits to a code word and send that code word, right? That's the simplest example of compressed forward. I mean, the reason noisy network coding and compressed forward got so much attention is because you can prove that you're within a bounded gap of the cut set bound. So you can prove that these methods are virtually optimal at high SNR in the sense of scaling. Of course, these gaps can be very big, so often you see papers saying, oh, the gap is 5 bits. Well, 5 bits is 15 dB. I mean, for a practical person, they'll say, why am I giving up 15 dB? And then if you compare to other strategies, often you might be giving up, who knows, 6 to 10 dB. Nevertheless, I mean, this is a very simple way of designing this function, just as an example. Now, the compressed forward itself is exactly this, just with vector quantizers.
Typically, given a source, let's say, so how many bits are you quantizing to? Typically to get
right.
Capacity, because
sure. Let's do an example. Let's do an example. So suppose this distance is 1, right? And suppose this distance here is 0.1, right? So we can now compute what the signal to noise ratio here is. Let's say it's 20 dB SNR here, whereas this guy has 0 dB. Well, we can quantize how many bits can we send from here to here. Well, it's usually this number divided by 3 approximately, so it's about 6 bits. So yeah, here I could use a 6-bit scalar quantizer, send to here, and again I'm getting a pretty accurate representation of what I received, and then that's how I'm getting this x1, y2 hat, y2 hat, y3 given x2. That will be my limiting rate now, right? Because the receiver has decoded x2, so it can condition on it. It also gets the 6-bit quantized version of y2, and so we have a 2-antenna receiver. Again, the gains won't be big, but if I have a 2-antenna transmitter, now the gains can be big, right? Because now we're getting a 2x2 system. Of course, now I might have to, I'm still giving a 6-bit quantizer. Not bad, right? So and now this guy could use precoding, right, to orthogonalize the channel, or even water filling on the... How do you do water filling on a quantized channel? Interesting question, no? right? So if this was a perfect channel, we would know how to do it. Take the singular value decomposition, water pour on the singular values, right? Now we have, suppose one of them has only a 2-bit accuracy or 3-bit accuracy. How do we do the water filling now? How do we do the, very practically interesting questions. For a company, could be very relevant, right? So yeah, so like I would definitely start simple, right? That makes a lot of sense. But developing a theory for that, it could be also fascinating.
Okay, if we consider, let's say, the same scenario of AWN with distance kind of thing or something like that.
Yeah.
What are typically, like, based on the location of the relay, what strategy? Like, this seems to work better when the relay is closer to destination.
Exactly, exactly.
If my relay is closer to source, maybe I will do decode quality.
Absolutely,
That
absolutely.
would my,
yes.
And in between I maybe amplitude, amplify forward kind of thing.
I think decode forward is good for most of the range. It's really only when you talk about relays getting really close to the destination. So just as a general perspective, decode forward is best pretty a long way, but you might have very disparate situations where you really have all relays only here and all nodes here, and then definitely everyone in here should be doing compression and everyone here should be doing decoding. I think that's the main insight. Yeah, but in terms, again, like, I think, there is interesting theory to be done there. Maybe one can find some interpretation of what the optimal processing is for such problems. That's just as a simple problem to study once, yeah. No, that's a good, one should be looking at toy examples, then you get ideas for research problems that might have some interesting outcomes. I think from a communications theoretician's perspective, starting with the small networks makes the most sense, of course. And most of the action has been in these problems, and in the communications literature has been like choosing functions like this and trying to optimize them, doing modulos, looking at a little bit of scaling for small networks. So it's a big area, but if you have an application, like if you work for a company and have like a concrete problem, then there's a lot one can do, because specializing all the theory to those problems is challenging, and building something is challenging. But the ideas, I think, insight is useful. Gives you many directions to go, many things to try out. Any other comments or questions?
So just last one.
Yeah, sure.
For generating channel state information, we sometimes use mean mutual information concept. So I just don't know about it. If you could put some light, like they have something like mean mutual information per bit and per symbol, and they used to map it to specific correlation schemes.
Min mutual information?
Mean.
Or mean? Mean mutual.
Mean.
Okay, so I'm not sure what that refers to. I can only guess. I don't know if it's right. When you say mean, I just think ergodic information rate, so average to over all possible. Is that what you're? But you may not know.
Just saw it in some comment.
Well, I think you're talking about channel.
How is
And
Well, you're talking about the problem where you have state, right? So, and the question is where is the state known? Is it known to the transmitter, receiver, or both, right? And if it's known to the receiver, usually you just get, you're just getting a I of x, y given h. Right, and that's an ergodic rate. That's the capacity you would have here. And now the transmitter has to choose usually IID kind of sending, because it can't control everything. In this case, it's water filling. So this is the usual case where we think about, like with fading, both guys know the channel, so you do a singular value if it's a MIMO channel, singular value decomposition, or if it's a time variation. Now it depends whether you know it causally or non-causally. In this case is the Gelfand-Pinsker problem. right, with non-causal. If it's non-causal, and if it's causal, then it's Shannon's theory. And in Shannon's theory, you see these trees appearing again. The only difference in Shannon's theory is that the trees look like this, and then you don't use the first piece. And that's called Shannon's strategy. Shannon's strategy is this tree without the first piece. Okay, but so I would need to know which case you're thinking about here to know. I don't know what mean mutual information is.
You know, the UE is getting signal, and it has to transmit the channel state information back to the network.
Okay.
So on the UE, they are generating channel state information using this concept of mean mutual information.
Mean mutual information.
Per symbol.
Okay, so I would have to see what that is, because I can only guess how that channel state information
after
is
that,
generated.
they generate some tables. They'll map it to certain modulation scheme,
Uh-huh.
and that will be fed back to the network.
To the network.
So, understanding information theoretically, how this is actually getting practically mapped to modulation and coding schemes.
Right.
is interesting.
So it sounds to me like you are measuring a channel quality that you're representing as a mutual information, and then looking up at these curves, this is BPSK, QPSK, 8PSK, and then you're probably, I'm guessing now, you're looking at you're mapping the channel quality into some number on the information axis, and then you're looking for which modulation you're going to choose, something of this sort. So there's probably some map made like that. When these things are done, they're often very ad hoc. Often, not always. Sometimes there's someone who really knows the stuff who will design it carefully. So it's probably best to check where that design came from and how. Usually you find a paper somewhere, right? Either in some conference like ICC or Globecom describing how this table was generated. Usually you can identify who did that. Also, if you look in standards document.
It boiled down to some Bessel functions. After that,
Bessel functions.
Yeah. So
Okay.
I lost
then
the view of how it all came.
Yeah, if it's Bessel functions, it sounds a little different than what I just described. Then it's
So the most curves are similar what you have drawn.
okay.
But after that, there were some Bessel
Yeah.
functions using which they were mapping. So
That sounds sounds like Doppler shift or something like that. So there you get the Bessel function correlation, and then if you look in the frequency domain, you get this spectrum, Jake's spectrum. So maybe it's some mix of those, but I can't answer that. I mean, when I think Bessel functions, that's what I think of in the communications context.